for a long period of time, all of a sudden I like run out of breath. So I might ask you a lot of questions. So if you help by talking back to me, you'll like chill me out. I can take some breathers. It'll be great. Okay, so if there are no questions, okay, I'll tell you things about me. Okay, so starting out, right, so my undergrad adventures brought me to this place here. So this, you're looking at it, I don't know, it could be the lake. It's definitely not the lake. It's actually the Arctic Ocean. It's near a place, well, it's right outside of Svalbard in their fjords. Svalbard, who's heard of Svalbard? What? Why? Somebody tell me you, why? What? Okay, let's hang out later. You back there, why do you know? Amazing. And who else? There was one other raise of hand. Yeah, please. And then you. Oh, so you're kind of like closer. Fair. And what about you? Gosh. Yeah? You were doing a cross country trip as much. Amazing. Wow, that's so cool. Okay, well, when I was 18, I had no idea that Svalbard existed. And I know many people who had no idea. So that's just amazing. That's really cool. So yeah, this is where I was about 2 years ago. And this was very cool for me because I study the Arctic Ocean. But I get horribly, horribly seasick. So I don't really go into the ocean. I like to look at observations from the ocean and think about things of how it works, but I don't go there. And I was invited to give some presentations, and it was so cool. And I guess those who have already been in the Arctic Circle know it's just a really interesting place. I remember after giving my talks, there was a big party, and we partied until like 3 a.m. And I remember coming home, and it felt like the afternoon. The sun just is never setting there, and it's just wild, wild place. Okay, so what got me there and how? Okay, so first, just like a little bit about me and about my research. As I said, I'm kind of like a seasick oceanographer, so I like to do my work from a desk. If it's outside and somewhere pretty, this is actually where I was for graduate school. This was my favorite spot to work from. And I like to think about all the changes that are going on in the Arctic Ocean. And the biggest one that many, many people know about now is that the sea ice is disappearing. We know we're on a warming planet, and that's changing things a lot. The ocean is heating up, the atmosphere is heating up, and this is changing the physics of how the atmosphere and the ocean is interacting with the sea ice. And so I'm really interested in understanding that from what can we tell from observations? How do we think about this mathematically and with the physics? And how well are we simulating these changes with climate models that are projecting the future? So that's kind of me. But that wasn't always me. I did not care about any of this stuff initially. I was all about tennis. I was a sports person. I was a bit, and to be fair, I'm still a tennis person, but now I'm on the sand, and I'll explain why. This was last year. This is this year. I think you can probably see why. Um, and so, yeah, when I was in your shoes, it wasn't about physics for me. I don't know if I would have been in this room. Maybe I would have. So as a high school student, I was going through, kind of sleeping through high school, and it was amazing. So I'm from the US, and you can kind of sleep through high school and get great grades. It's amazing. I don't know if that's totally true here, but in the US it totally was, up until my physics class. And so I got into my physics class, I totally bombed my first quiz, and it just woke me up. And all of a sudden I was like, okay, this is interesting. And so my eyes were opened, and I was paying attention for the first time, and I really started to enjoy it. So I got a sense maybe a physics major was for me, but at the same time I thought, what do you do with a physics major? And I didn't think I just thought you become a physics teacher because that's all I had seen. And it's just so much more to that. And now I'm super curious, like, would somebody be willing to share why they're kind of interested in physics already? I know that's such a hard question. Yeah, research. Anybody else who's kind of already like research might be cool? Oh my gosh. Okay, and do you have like a sense of like what field you might find interesting? Just raise of hands if you think like, just, yeah, sort of. What about people who are like, I have no idea, just something physicsy? Cool. Who like sailed through their first physics class in high school? It was like piece of cake. Just like feel good. Who had some issues? Nice. Cool. I love that. Okay. So yeah, I kind of went through the same sort of experience where eventually, well, I wasn't as on top of things as you all were. Eventually, I got a whiff of the idea that, oh, okay, research exists. And so for me, this turning point, so this is kind of, I just thought, okay, let me go back and think about what happened to me in undergrad and put some pictures together. So this is kind of like my outline for the talk. It starts here. So this is me playing tennis on my university team. And there's an ice cube here. It has nothing to do with sea ice. I'll explain later. And a few of the different adventures I went on, all by essentially traveling by internship. And so I think if I want to leave you with anything today, it's this idea that trying out different internships and just kind of listening to your gut and doing weird things, I strongly, strongly suggest that. And I'll explain why. So, okay, so we're starting here. I'm playing university tennis. I know I like physics, but I did not have any idea what my major would be because I had no idea what physics majors did. So I was thinking maybe engineering, maybe biology, maybe journalism. I have no idea, but I'll just take classes and I'll figure it out, I hope. Meanwhile, surrounded by people, and I'm sure you know them, or maybe you're one of them, already kind of knowing exactly what they want to do with their life. But those things change too, and you just kind of figure it out. So, okay, so I'm here and I kind of like physics, but the truth of what's happening is my focus is tennis. I'm actually there being paid to play tennis. That's how I'm paying for these crazy universities in the US. Like, this is my focus. And then in my second semester, I slip on some ice and I break my foot. And all of a sudden, things change very quickly for me. Well, slowly but quickly. It was the whole thing where the doctor thought this bone was naturally in two pieces. I played on it. He's very grumpy with me because he's paying me to play good tennis. I'm grumpy with him because my foot hurts. And it's this whole thing. And as this is happening and it's crappy and it's like, you know, you kind of, as you're growing up, maybe, at least for me, you're starting to kind of figure out like who you are and what you're about. And maybe it's very diverse and it's a lot of different things, or maybe you honed in onto one thing and you're like, this is me. And so I kind of had that with tennis. And then all of a sudden this foot just like was not working. That's why I play on the sand now. So this foot was not working. And all of a sudden at the time it was like the worst thing ever. But then it kind of opens you up to all these different possibilities. And so I'm kind of like dropping this in for you now because maybe you want to break your foot without breaking your foot. Okay, so don't like hurt yourself or anything. But you know, if you do this thing where you have to let go of the whole idea of what you're about and be open to something new, this is totally the place to do that because you can kind of mess around and you have no idea what you're doing. Right? Like I'm kind of in that place right now. I'm pregnant at this first time, so I can make all the mistakes I want. I've never done this before. Maybe this was a horrible idea and I'm going to run out of breath soon. I don't know. But you're like that right now. So you're here doing university for the first time, and you can just make all the mistakes you want, and it's fantastic. It's like the fastest way to learn. So anyway, so back to my story and stop giving you advice. So, right, so I've broken my foot. And everything's such a bummer. And I kind of feel like I'm going back to what happened in high school, where I have to still really focus, not too much on a lot of the other classes, but physics. Physics, I have to really pay attention. And it becomes this kind of beautiful escape whenever I'm doing my physics homework, because it's really the hardest class for me. So I'm sitting there and I'm trying to understand everything. And it's hard. And as I'm trying to understand it, everything else kind of disappears. The foot disappears, the tennis disappears. And I'm just thinking about how I'm thinking about reality, right? Because physics is telling you kind of how things move, how things work in the most real sense. So I feel like I'm escaping, but I'm connected to reality at the same time. There's something good happening here. And so I keep finding myself like, oh, get me off this tennis court and like get me with my physics textbook, which is kind of weird. Um, and so after my first year, I'm in my second year now. I start to, and you'll see this year, I think, you'll start to see all these opportunities kind of pop in front of you of these different internships. And the first ones I kind of ignored in that first year because I was like, I have to focus on my tennis. But then all of a sudden year two's coming and it's looking more and more interesting. And so I fully encourage you to just start to, even if you smell something that's just like, I don't know why, but I kind of want to see what this is about, just throw your hat into the ring. You never know what's going to happen. And so that's what I did. So I spoke with my physics professor and I said, hey, I'm interested in doing this. I'm going to apply for this program. He said, okay, go for it. And what this required was like, okay, I found a program I thought was cool and I have to write an essay. And I just like wrote an essay and I pretended that I was never a tennis player. I'm just like super into physics since I was like a little kid, which is just like a complete like fabrication. And he said, no, this is wrong, like try again. And what he said is, first of all, not one, 10, choose 10 different programs. That's a good lesson when you see this, because these things, first of all, you don't really have much to show for yourself just yet, even if you were an amazing high school student. So try 10, because it's a lot luck of the draw. And then the other thing is, he said, talk about tennis. And I thought this is a great lesson looking back to it, because even if you're kind of on a path and you know exactly where you're going, and then you completely change it, and you know, at the time I thought, oh my gosh, all this time and energy wasted. But no, you're learning and developing all these skills that are transferable. And that was kind of my first lesson into that. And so he's like, talk about tennis, talk about the different things you've learned, how you've learned to kind of be disciplined and go after something, and say you're going to apply this to physics. So I did that and I applied to 10 different schools. It was the last time, I think, yeah, this would have been the last time I did this, where I actually got like the envelopes out and like printed everything out and like did it old school. And out of the 10, I got into one. And so that's why the 10, great, always do 10. And that one brought me to San Diego, California. So this is me on the beach in San Diego, a place I would return to. Some cool pictures there. And so I did my first internship, and this is actually my first slides from my first presentation as an undergrad. I was on Big Bang nucleosynthesis, which is like a mouthful. Maybe some of you already know some of these things. I showed up, I had no idea, you know, I just kind of had taken 2 introductory physics courses and an electromagnetism class, showed up, and they said, okay, you're gonna do theoretical astrophysics. I said, cool, great. And this looked so weird because I was like, I don't really know what research is. What does that actually look like from day to day? And I showed up, and apparently I kind of got what you get as a first-year graduate student in this field, which is just like a pile of books and go. And it was such a weird and interesting experience. And I remember the whole time being very worried that I was doing it wrong, because I was like, this can't be what research is. I'm just sitting here reading, but also really enjoying it. Like, I just thought it was the coolest thing ever, learning about all these different topics. You know, I'd go through these books, I'd get like a pile of questions, and then I'd get to chat with graduate students, and they would kind of teach me. And it was really cool. All the while really worried that I wasn't actually doing research, and everyone kept saying to me, no, this is research, you're doing great. And now, I don't know if it's kind of true, learning is a part of research. It's also not quite research yet. You're not doing the new thing yet, but you're kind of pulling in your information and starting to get curious about questions. Maybe they're open questions, and that's real research. Maybe they're closed questions, and so that's, you're still kind of like building the skills. So that's what that looked like earlier on. And I just loved it. And I thought, okay, that's for me. I'm going to do astrophysics. And so I'm now in San Diego, and I'm doing this weird thing. And now I'm back to my personal life, right? So I've done this summer program in San Diego. It's so cool. I love it there. I've got this broken foot. So like, what am I going to do? You know, I can go back to my old university, but why? I'm not going to play tennis there. I know I love physics now. I want to do astro. It's not really an astro school. So I find a way to kind of just hang out in California for an extra year and take classes. And it's a weird thing to do because I cannot graduate from there. Because if you are an out-of-state student, that tuition is just massive. Not really a problem for Canadians for the most part, I don't think, but it's a real like US issue. So I'm there and I'm like, okay, I'm just gonna figure out my stuff. And I'm hanging out, I'm taking classes, and it's so different and interesting. My physics classes at my first university, 10 students each year. This one, it's about 50. I think at U of T, it's like around 200 more, 400 each year for 131, for 151. Wow, and then by graduation, we'll find out. Only time will tell. Yeah, so it was a very different experience. I'm taking these classes more and more. I'm like, astrophysics, physics, this is cool. And then the summer's coming and I'm gonna do the same thing again. Okay, 10 applications and I'm gonna find another internship. And as I'm doing that, I'm with a friend and he's been taking ocean physics, which I didn't even know was a thing. You know, I'm getting all into like quantum and stuff. I think neutrinos are super cool. I'm like, what could possibly be interesting about water? I don't know. But he said, yeah, just apply for this thing. It should be really cool. It's called Woods Hole, which I thought he made up, but all of this real. Okay. So I apply for it and it's the one I care the least about. I remember I applied just before the deadline in my pajamas. I don't even think I proofread it. I just kind of like stream of consciousness, like this would be really cool. I've never done this before, whatever. And that's the only one I got into. So I had a chance to stay in San Diego and keep working with my supervisor there or continue this adventure by internship. And I just go for it. I say, you know what, let's try. Let's see what this oceanography thing is about. And let's see, here are my pictures over there from this. So this brings me back to Cape Cod, Massachusetts. So it's like the little tail that sits off of Massachusetts, the state like in the Northeast. I don't know what Canadians know when it comes to geography. I'm sorry if that's too much explanation. And it's interesting. So now I'm starting to kind of really do research. I've been given a data set. I'm learning to program. I'm learning to look at what the ocean really looks like. But at the same time, it's not really resonating as much as astro. There's something about astro, right? It's beautiful. Like your head's in the stars. You're thinking about the universe. And this, it's like, okay, it's water. It's the ocean. I'm not quite getting it. But I'm trying and I'm learning new skills. Like, let's try. And then I was told, well, okay, hey, while you're there, go to this thing called the GFD Summer School. And it's actually a program for graduate students, but it's really cool. Talk to them, meet them. You're gonna learn cool things. So I go to this summer school. It's on the same campus of where I'm doing this internship. And it's this tiny little cottage with blackboards like all the way around the room and these super old desks from like the 50s. And it turns out this is where the mathematicians like to hang out in the summer. And they're really more about the theory and the math. They're doing some experiments too, some simulations, but they're more about the math above everything else. And something about that's kind of hitting me. So sorry, I'm using the word GFD, geophysical fluid dynamics. So I'm watching, I'm listening, and something's starting to resonate again. There's something about the math that I just like. And then every day they're doing different presentations. So I'm meeting these students, I'm listening to these presentations, and this woman comes, this professor from California, Santa Cruz, California. She comes and gives this talk about astrophysical fluid dynamics. And there's something about that where I'm like, okay, there it is. There's the astro, there's the fluid dynamics, these concepts kind of coming together. I think that's what I want to do. And she's talking about the fluids of the interior of stars and planets. And I'm just like, this is it, this is it. So at the end of her talk, I go up to her and I say, hey, are you interested in hiring an intern? So a little bit different from the 10 applications. I just chat with her, and for some reason, she hires me. And it's interesting. She's kind of at this interface of astrophysical fluid dynamics, but she can also do geophysical fluid dynamics and think about the ocean. And she's just tuning parameters to decide what she's doing. And this is my image from this. This is actually an image from my first paper, which I wrote with her. Let's see what's next. And I want to, from there, go into a little bit of physics. So I've been talking about myself a lot, but what I really like is salt water. So what I'm going to do is just take a quick interlude away from the story, tell you about these cups of water, try to connect it to astrophysics and back to the ocean. We'll see if we can do it. So, but first I'll lead with a question to you. So if we have 2 cups of water, both well mixed, so you've taken a spoon, you've stirred it all up, one's filled with fresh water, one's filled with salt water, both have ice cubes. Which one's going to melt first? Raise of hands for the fresh water. 1, 2, 3. Cool, okay, like about 5, 10. Salt water? 1, 2, 3, 4, 5. Wow, about 50-50. And a lot of people, and who defers the answer? No answer, please. Okay, cool. So this is, and who's seen this before? That's it, awesome, cool. Okay, so I'll tell you, when I first saw this experiment, I was 100% sure it was the salt water, because I'm from upstate New York, and just like in Toronto, we just throw salt everywhere to melt ice. We know it changes the freezing point, and so ice will melt faster in salt water. So I just thought 100% salt water. It's obvious, yeah? Okay, so let's see this actually play out. So here's a little experiment. We're doing exactly that experiment with mason jars. So we've got salt water in one jar. I've tried to pour a ton in there so you can see it's actually getting cloudy. And the other one is fresh. Now you're gonna have to really focus here because there are cats in this video. So do your best. So we've got 2 blue ice cubes. You can do this at home. Put it in a spoon and just really gently let it drop. And what's cool about this is if you make these blue ice cubes, you can see where the melt water is going. So you can kind of see, I love this. I just think it's so beautiful. These little dye dropping straight down. And here in the salt water, it's staying up. Can somebody, yep, there's a cat. Can somebody tell me why in this mason jar, why do we see these little strands going straight down? Yeah, why? Almost. Does anybody have another? So the guess was there's no density differential between the melt water and the ambient water. Yeah, back here. That's it, exactly. So it's pretty much the same as when you boil a pot of water, right? So you put your pot of water on the stove, you're heating it from below, and that water is at the bottom heating up, so it's warmer, therefore lighter, less dense, rising to the surface, the cold water going down. So same thing here, so that ice melt is gonna be near the freezing point, therefore colder, just like the air where it's circulating this way as well. So that cold water is heavier and then falls straight down, and the warm water is starting to replace it. And so what we're seeing here is this cup is fairly well mixed. The other way around, cold water is heavier, just like cold air is heavier. Yeah. Yeah, that's liquid water. That's right, that's liquid water. But once you've changed your phase state, then basically what's happening is everything gets kind of stretched out, right? Because you have these structures that are forming inside the ice block that makes it less dense and then it floats. Yeah, that's exactly right though. Once you have a phase change, whole new set of rules. Can somebody tell me why we're not seeing this in the saltwater case? So you can see right at the bottom here, there's this, like our blue cloud just kind of ends and then it's at the bottom. Yes, all the way in the back. Yes, exactly. That's exactly right. So basically, we have the same setup. Cold water is heavier than warm water, but that cold water is coming from that ice cube, and that ice cube is fresh. We didn't put any salt in it. And so there's enough salt in the ambient water that makes it heavier, so it can't get past it. Okay, and so what you can see here almost, well, you can't really see the ice cube in here, but you see all this stratification. This one's gotten very tiny, and at the very end, you'll see the different sizes. But you get all this mixing, so all this warm water is coming up and interacting with this ice cube, while here it's separated. It's being isolated from that warm, salty water. It's protected. It's able to last longer. So it's the salt water that sticks around. Okay, question for you. Which one is most like the ocean? Who thinks it's the freshwater one? Saltwater one. Ah, you're all wrong. No, I'm kidding. Yes, the ocean is very salty. It's kind of a trick question. The answer is it depends. So if you go in the mid latitudes, so further south, not in the Arctic Ocean, it's much like the lake, right? So if you go in the lake, right at the surface, it's nice and warm, and then as you go down, 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 you're away from your heat source, the sun, it's colder. Yeah, and so it is temperature controlled. Oh, sorry, and this is me showing you that one, the ice cube is gone, and the other one, it is still existing. Yeah, so the mid latitudes are actually a lot more like the freshwater ocean, meaning that the density is controlled by temperature. In the Arctic Ocean, on the other hand, in the polar oceans, it's salt stratified. It's like this, oops, let's see if I can move it. There we go. It's like this saltwater one. Meaning that if you take an instrument or a thermometer and measure what's going on, the temperatures in the polar oceans, what you'll very often find is cold at the surface, and then as you go down deeper, deeper, it'll actually get warmer. Not super warm, not like room temperature 20 degrees warm, but above freezing warm, like 1 degree. Where is that? I'll come back. Where is that heat coming from? Sorry? This is one of the sources. Yeah. So for example, in the Arctic Ocean, several thousand meters deep, at the very, very bottom, you're getting some geothermal heating from these vents. Closer to the surface, you're getting heat from the Pacific and Atlantic Ocean. So these oceans, they're going to be warmer because they're further south. They're flowing in, but they're also saltier. So as they flow in and enter the Arctic Ocean, they're going to subduct below those cool, fresh waters. And this is something in my world, we care a whole lot about that because you've just got all this heat sitting there, and there's enough heat contained in these waters that if it were brought to the surface, it could melt all the sea ice. And those waters are getting warmer, and they're moving closer to the surface. And on top of that, the sea ice is disappearing. So the sea ice, it's kind of like this lid on top of the Arctic Ocean, and it's protecting it from the wind, right? You can imagine, like, if you're sitting in one of these cups and I've just completely frozen the top, there can be all sorts of weird things going on there. You're protected. But as soon as that layer breaks away, the wind is going to start to stir things up and mix things, just like spoons are stirring and mixing things up. And so now all of a sudden it's easier to interact with those warm water sources from the Pacific and Atlantic. That's where my brain is all the time. Okay, right. So this is just a cartoon explanation of what we talked about. So in the fresh water, the cold water is heavier. Cold meltwater is heavier and moves down. The warm water is lighter and moves up, and so you get mixing. But in the salt water, you're colder but fresher on the surface and warmer but saltier at depth. And it's the salt that matters here. And so that's why you get a stable situation. Okay. But it turns out everything I asked you was also a trick question, because you could imagine that if that water, that salt water, was boiling, it wouldn't really matter how salty it was. The boiling water would melt the ice cube faster, right? And so what really matters is this relationship between the temperature gradient and the salt gradient and how that controls the density. So here's some numbers you don't have to worry about, but all it's telling you is how much does the temperature control the density gradient? And in this case, if you're warmer as you go down, that's an unstable gradient. It wants to overturn. And then at the bottom, you've got the density as it's controlled by the salt. And here it's stable. As you go closer to the surface, it's saltier. And so that's a stable condition. So the bigger that number is, the more stable your system is. So if this number is very, very small, and this denominator is very big, you're in the stable case. If it's very, very large, you're in the convective case. And then there's this funky thing in the middle called the double diffusive case. And I'm going to explain that a little bit. Oh my gosh, I'm running out of time. I'm so slow. Okay, I'm going to explain it quick. But I just love it because we've been just talking about salt water and ice this whole time. And there's been, I think, some surprises, I hope, at least for me. And it gets weirder. And this was kind of, going back to my story, this is kind of what was setting me on this path, was like, oh my gosh, I thought I needed like neutrinos in my life and stars and galaxies to be really interested. I just need salt water. Like, this is really just fascinating. And I see myself kind of, again, disappearing into the math and physics and loving it. And this is all in this, during this internship that's about astrophysics, but this was the foundation for the science that I was doing, and it all came from oceanography. So it's just super weird. Okay, so I'm going to tell you quickly about this little middle case here. You're not stable, you're not convective, you're somewhere in between. It's called double diffusive convection. And before I tell you that, I have to tell you about single diffusive convection. So now let's think about our case with the salt water cup. So we've let it sit for a bit, so that means the salt is settling. You're saltier here, you're fresher at the bottom. And what you're going to do is just kind of knock this cup, and this is kind of like this thought experiment, right? Because we're not going to see this visually, but if we knock this cup, you can imagine, okay, there's a parcel of fluid that's a little bit heavier, right? You've given it a little knock, it's moving around. This parcel of fluid's a little bit heavier, and it moves up into the region where there's less salt and it's less dense. So now it's surrounded by less dense fluid, it's going to fall back down to where it's more dense. And all of a sudden, you've set off an oscillation just like any other, just like the pendulums you think of or the springs, and you go up, down, up, down. And these are waves. Yes? Yeah. Did you say you had a question about ions? Oh, geez. You know I hate chemistry. But I tried. Yeah. That's so interesting. I cannot answer your question because I really don't know much about chemistry. I think the answer is yes. If you're curious and interested about these things and you move into the world of sea ice, it's gorgeous and confusing. So I encourage you to dig into that, and I think you'll find a world that's going to blow your mind. But I can't help you at this point in time. Yeah, not a major factor in like in this particular question, right? But if you get really curious about something else, for example, how and why ice forms in different configurations and under different conditions, and you see like it's really cool. You have these things called like frazzle ice and pancake ice, and it's gorgeous and it matters because it impacts how much energy from the wind is going into the ice and ocean, but also how much heat's getting transferred. So, you know, how sea ice is evolving over the course of the season, which is changing with the decades. There's questions where that matters. This particular one of when it melts first in a cup, probably not. But that doesn't mean it doesn't matter. Uh-huh. Okay, so now let's add our second component. So now we're into double diffusive convection. So we're not just diffusing salt, we can diffuse heat. So we're adding this temperature gradient. So now still salty at depth, but also warm at depth, and then cool, fresh at the surface. So here's the key that makes this weird and funky. Turns out heat diffuses 100 times faster than salt, okay? So we're taking our same cup, we're knocking it, and we've got this fluid parcel that's kind of cool, fresh, and we knock it down. And so it's cool, fresh, but it's in the warmer, saltier region. But it's gonna lose its coldness quickly because heat diffuses 100 times faster. So now all of a sudden, it's fresher than its surroundings, but it's got the same temperature. So it's lighter not only than its current environment, but where it started from, because it's got all that extra heat. So we start off that oscillation, and instead of returning to its initial position, it's going to overshoot. And so with it, it's bringing its initial saltiness, roughly, but also all of that heat. And now it's much heavier. It's going to quickly lose that heat, because that's what happens. 100 times faster than salt, it quickly loses its heat. So it's getting colder, but it's also already saltier. So it's much heavier, and it's not just its current environment, but the environment it just came from. And so it drops even deeper, and so on and so forth until you get turbulence. And this is double diffusive convection. It's kind of funky. It gets funkier. So this is just the initial instability. So you're starting with something that's technically stable, right? We didn't see any turbulence in that second cup. We just saw warm, salty water hanging out, cool, fresh water hanging out, but just a little knock, and you can get turbulence. And this turbulence can can give you these really funky structures in temperature and salinity called staircases. And there they are. This is the example. So we're seeing how temperature evolves with, temperature, salinity, and density evolves with depth, and you get these steps. So every straight line, it's got all the same characteristics of temperature, density, salinity, and then a quick change. And then the same characteristics, and then a quick change. And the reason for this is still highly studied, and that was part of my research project. And it was just fascinating. I just kind of loved that, you're going for something, a very turbulent situation, and all of a sudden something very coherent kind of emerges from it. And why is that? And trying to understand the math of what we think is going on. Okay, so we're almost towards the end here. I want to bring this back quickly to astrophysics, which is where this started, right? So, and I think back to this professor now, and I'm like, wow, she was so patient. This was definitely an oceanographic question, but she brought it into astro for me, and this was kind of the analogy of how she did it. And so we're going back to the situation again with the cups, but now we've got two cups, one where we're sprinkling in salt water, and one where we're dropping a salt chunk. Okay, so same amount of salt, but one is sprinkled, one is a big salt chunk, and we're heating it from below. So we're adding that temperature gradient in. Now, in this situation where you're sprinkling it in, well, it's all well distributed, right? And so when you're heating it at the same time, this stays well mixed. Whereas your salt chunk drops to the bottom, and that's going to set up that strong salinity gradient where you can get these staircases coming in. And so now all of a sudden these staircases can kind of tell you a history of what's happened. How was the system formed? And so the idea, the analogy going into astronomy here is, well, maybe we can do the same thing with planet formation, where the sprinkling of the salt chunks would be like a planet being formed by small planetesimals crashing into each other and clumping together, whereas the big salt chunk would be a large planet-like or rock-like structure, and then the atmosphere coming afterwards. And that's all I can really tell you about that, because I went in a different direction. So I love this, and I love that I was still doing some astro, but I was realizing more and more, like I love the idea of really measuring things, and this is not something you can really measure in astro. So I don't even know what my next slide. Okay, so here's my presentation from there. It was fantastic. Lots of math, lots of numerical simulations, lots of pretty movies. I loved it. And here's a numerical simulation for this, where you can see, I'll show you real quick, since we've now talked about it so much. Let's see if I can find it. So I'll start it from the beginning. There's going to be an instant where you see all these straight lines. You can almost see them starting now. That's that initial instability, that overshooting oscillation. And then you're going to see a mess. And then all of a sudden, you're going to see these really coherent layers kind of emerging. So cool. So I adored this. And let's see, you got 5 minutes left. I want you to see these layers, because they're just so, so cool. There's a few more, and they start to merge. Gorgeous. Okay. Onward. So, okay. So that gets me to the end of undergrad. And it's, again, just kind of like following these paths. And I keep doing some internships. I don't want to get too much into them, but I will say Continuing these internships brought me next to Australia, where I got to do, I still was like, I couldn't let astronomy go, right? And I tried it a little bit more, and I got an internship in Australia, and then another one in New York City at the Museum of Natural History. And they were cool, really cool internships. But it just wasn't hitting me like this project with double diffusion did. It was, I think it had to do with the fact that this project, it kind of scratched that itch of it. I felt like I was working with something real because I knew these staircases existed in the real oceans, but I was still getting to do a lot of physics and math. And so it was kind of hitting that itch. Whereas when I was doing more astronomy, it felt like there was a bit of a separation there where either you were really into the observations or really into the theory, but the theory was really hard to test. And the observations, there's just less theory going into that because there's already enough to deal with in terms of just getting those observations in the first place. And so things came to a head for me, and I had to kind of make a decision of which way I would go. And I kind of decided, okay, I want something with physics. I love fluid dynamics. I love that kind of physics, and I want to be connected to nature. And I really felt, especially from the museum, I wanted to be connected somehow to society. And so something that was closer to climate change seemed to kind of hit all of those. And that's what brought me to San Diego for graduate school and eventually here. So I don't have time. I had a few more things to explain about how sea ice works in the ocean, but that's okay. I want to quickly just show you a little bit about what my work currently is. So I like to, as I explained, look at climate models. I also like to look at observations from the Arctic Ocean. This is a wonderful example of what I use a lot of, ice-tethered profilers. These are instruments frozen into the ice with an instrument running 800 meters down, running up and down and taking measurements and sending a text message. And it tells us all about the ocean. It's amazing. This is historically a very difficult area to study, and now all of a sudden we've got 20 years of data there. I also love to look at the super old data from the 70s, where there are essentially people working as human ice-tethered profilers, living on the ice and drilling holes and throwing down instruments up and down, taking all of these data. And so just trying to understand, how is the ocean changing? How has it been changing over the last few decades? And then I just love my lab experiments too. So here's some numerical simulations with students I've been working with. A little lab experiment. This is the first one that I did with a professor at UCLA, adding rotation. So I've had a couple students now really diving into this work of what's going on with when you add rotation, because of course our reference frame is rotating. So I have a student working on this in the lab, but also looking at numerical simulations. I've got a much larger lab shown here where I tried to blow up this experiment in a saltwater pool in Manitoba. There's one in Winnipeg, and there's one that's just opened in Churchill. So we've done some outreach and started some research in these areas where you're kind of a little closer to reality because it's larger. And then still looking at different climate models and how well they're able to capture these changes. So specifically looking at the Canada Basin, and now I've got a student looking at what's going on in the Iceland and Greenland seas, and just finding it's a big mess and there's lots to do there. All right, so I think I will leave it there. And hopefully if you have questions, yeah, this is my roundabout. I think that's the last one. And maybe I'll put some videos on for you if there are any questions. Thank you so much for listening to me.
Hello. If we have any questions, just after the presentation, please ask them into the mic here. Does anybody have any questions? Oh, okay. I think you raised your hand first, so.
So on the whole double diffusion process and all that, does the supercondensation of Arctic water like affect that in like the physical systems in any way?
No, there's no there can be in everything I've spoken about today, no superconduction.
No, it's not superconduction. Supercondensations, where colder water remains liquid because it is oversaturated with salt.
No oversaturation with salt with these. That's
Mm.
can be a thing, but not with anything I've discussed here.
Mm.
Yeah.
All right.
Thank you. And you had a question also?
Yep. Hi, my name's Hayden. I'm planning on doing a specialist in mathematical physics,
Cool.
and I have background in doing a couple harmonic oscillator simulations, and also other kinds of simulations related to particle physics. And what really interested me was how you did those numerical computations and simulations for the double diffusion. And I'm just wondering what kind of methods did you use to perform the simulations, and how is it structured?
Gosh, that was so long ago. That
Sorry.
paper was in 2011. I think it was a spectral code. Yeah, if my memory serves, it was a spectral code. And beyond that, I don't remember the details of it. I'd
No
have
worries.
to send you the paper.
I don't remember anything from 11 years ago either, so that's fair.
That's a cool area, though. Coupled oscillators were like one of my favorites.
Yeah.
Okay, anybody else have any good questions? Okay, I think we have one more.
I assume in your current research on ocean sciences and all that, you use numerical simulations. What kind of programs or computing languages do you recommend to learn for such things?
That's a great question. So I like to personally use mostly MATLAB, but right now the standard is Python, and most of my students use Python. And that's actually what you'll learn in your classes, I believe. Starting in the second year, or do they get some in the first year too?
You get a little bit of Python in your first year practicals, and then a lot in the second year labs and all the labs after that. And of course, PhySU runs a Python workshop, usually first semester, 2 of them. So come to that as well.
Amazing. Yeah, and this thing is huge. I feel like for me, thinking back, doors just start to open once you understand how to program, and then you can really dive into doing research. Great question. Thank you.
Okay, I think we're a little over time, but final call for questions? No? Oh, okay, one more. One more? Do we have one more?
Totally. Sorry, I went on way too long. I'm
No, it's great. It's great.
Slowly than normal. I'm more scattered in my brain.
You seem like an amazing professor. Are you
Okay.
teaching any classes this year?
No, I'm about to have a baby. I was teaching, so actually, thank you. I appreciate that. Thank you for the compliment. So I started teaching here last year, and I taught Physics 131, which I think none of you would take as intended physics majors. And I don't actually know, I'll be teaching more classes when I come back, but I don't know what they are yet because they haven't been assigned. I'm hoping it's in the realm of fluid dynamics, but we'll see where I end up. But I will be looking for interns when I come back too. So if this stuff was resonating and you see opportunities, I strongly recommend applying for everything, including here, but also around. See if you can travel a bit. It's super fun. But yeah, I'll be around, just not this year. Mat leave starts for me on Monday. So hello and goodbye.
Okay, thank you very much. Another big round of applause, please.
Thank you.
And we have tea and timbits outside. They will be served again in the lounge right now. If you would like to come, would you like to come also?
Yeah, I'll be
Okay,
there for a little
perfect,
bit. I have
perfect.
a few minutes.
Just not very long, but half hour or so. Well, you can stay as long as you would like, but that's how long we'll be there. Okay, thank you everybody, and thank you to the people online
Nice
also.
meeting you all.
Goodbye.